Let's get started. Welcome back for those of you who were in the first session, and welcome for the others who just joined the second session. Can you hear me? Okay. So second session is a little bit more advanced. It deals mostly with the deployment aspect. So we'll discuss first the role of IGP and IBGPs. We'll discuss about aggregation, receiving prefixes, what we need to do to receive prefixes from our peers, essentially, or customers. And we'll discuss about origin validation, AS origin validation, which is security mechanism, RPKI. We'll discuss about preparing network and some configuration tips, general tips, not in this particular presentation as well as in the previous one. I tried to remain to be vendor agnostics. So most of the configuration tips are generic. I may give you examples mostly from iOS 6R, but in most cases they are just generic examples. So IGPs, so an example is ISIS or OSPF. Those are the two widely used IGPs by network operators. They scale, the reason for that is they scale better than the other distance vector protocols such as RIP. And they have a lot more set of features, including support for traffic engineering, and a number of other features that are not available on the other routing protocols. So it's typically either ISIS or OSPF. And which one is better? That's typically a religious question. So whoever uses it, they use it because it is much better for them in general. So IGP is used for carrying infrastructure addresses as well as just only infrastructure addresses. So the infrastructure address includes interface IP addresses or loopback IP addresses. In some cases, some service providers do not even advertise interface IP addresses; they just advertise loopback IP addresses. But in most cases, it's used to advertise interface IP addresses and loopback IP addresses. The goal is to minimize the load on IGP because, as we discussed earlier, when we do BGP, we use recursive lookup. The first one is BGP lookup. Second one is IGP lookup. Typically, if you have a link failure in your network, IGP is impacted, BGP is not impacted significantly because you are receiving routes particularly for the external routes. So if your IGP converges faster, it means your BGP traffic is also converging faster because of the recursive lookup behavior and because of the data structures implemented by most vendors to implement the forwarding. So it's important to minimize the load on IGP so that IGP converges faster, so that BGP converges faster also. So BGP is used both internally, IBGP, and externally, eBGP. IBGP is used to carry some internal prefixes, so usually prefixes such as, we'll discuss in more detail, but customer prefixes, modem prefixes, and so on. They are not usually used to carry, even though you will be carrying also the rest of your infrastructure prefixes, the routing table will prefer IGP over BGP. So if you have the route in both IGP and BGP, the route in BGP is preferred for local routes. eBGP is used to exchange prefixes with other ASs and implement routing policies. Most of your routing policy is applied on eBGP, even though you can apply policies on iBGP, and some do. Again, back to the model that we discussed earlier in the first session. Within each AS, you will have IGP and iBGP, and between ASs, you will have eBGP. That same model remains the same. Very important, BGP versus OSPF ISIs, do not distribute BGP prefixes into IGP. That's a no-no. Do not advertise BGP into IGP, because IGP doesn't scale to the same level of routes as BGP. IGP converges faster, but it doesn't scale in terms of number of routes. And there is no need to do that. So do not distribute BGP prefixes into IGP. Also, do not distribute IGP routes into BGP. In some cases, you may need to do that. There are other alternatives. It's better to do the alternatives instead of doing the distributing IGP. If you ever have to do IGP distribution, then make sure that you apply the right policy to filter out unnecessary prefixes from IGP into BGP and set the relevant BGP attributes when you are distributing. And also, do not use IGP to carry customer prefixes. For customer prefixes, put them into iBGP. Do not put them into IGP. It's not really necessary. Okay, so use iBGP to carry customer prefixes, not IGP, but iBGP. If you have a customer that is basically single-homed or that's directly connected to you using a single connection, you do not need to run eBGP with that customer. You can just point a static route to that customer and inject the static route into BGP, into iBGP, essentially. So you do not need to, in that particular case, you do not need to run any eBGP with the customer. You just inject it using a static route and a network statement. By doing that, whenever the interface flaps with the customer, the route doesn't flap. And that doesn't hurt you, because if there is a reachability issue, traffic will come to that router that injected the static route and will send unreachability information. So it shouldn't be a problem from that perspective. You don't need really to withdraw it. Consider eBGP with your customer. This is from an operator's point of view. So consider eBGP with your customer only if the customer has its own assigned prefixes from RIRs, as well as its own assigned ASNs. So if you have a customer that's using an address space from your own address pool, you do not need to run eBGP with that customer. You only need to run eBGP with a customer if the customer has its own assigned prefixes from RIRs, as well as assigned ASNs, because that customer may have, and also if the customer is multi-homed. That means if the customer has a peer, not just with you, but with other service providers, it's important to have that eBGP peering. So next one is aggregation. So aggregation refers here announcing the blocks that are assigned to you by RIR. So the aggregation on the reverse side means if you split or deaggregate the addresses that are assigned to you by RIRs into sub-prefixes, that is deaggregation. It may be necessary. Normally, it's important to when you advertise to your eBGP peers, it's important to advertise the aggregate prefix. Do not use sub-prefixes unless you want to do some kind of traffic engineering. And if you are multi-homed and do want to do traffic engineering, you may have to use sub-prefixes. There was a session yesterday by Joe Houston. It's a very interesting discussion. So BGP in 2013 that discusses the trends in the BGP table size and so on. So what his assertion is, the aggregation problem, the deaggregation problem is kind of subsiding. The BGP table growth is becoming more linear instead of exponential, which we had experienced for quite some time in the past. So it's not as much a problem as it used to be, and also the routers are scaling much better because of the obvious silicon growth. So it's not as much a problem as it used to be, but still it's important to minimize the amount of deaggregate routes. Okay, so the only time you want to advertise sub-prefixes is when you want to do multi-homing with traffic engineering, and we'll see that later on why you will need that. But in general, if you do not need traffic engineering, let's say you have one prefix assigned from RIR. If you advertise that prefix through multiple peers in the same way, then you may end up receiving all traffic through one peer, right? Because you only have one prefix, you don't have any mechanism of influencing which one should be preferred. So when you have that type of scenario, you may need to split into 2, 3, or 4 prefixes and then advertise sub-prefixes, some of them preferred on this, some of them preferred on this, so that you will have traffic load balanced across multiple peering points. So that's the only time you will need deaggregation or sub-prefixes of a block. If you have multiple blocks, then you don't need actually to do the sub-prefixes. You can use one block on this side, preferred another block, preferred on this side, and so on. So in general, and there was also interesting discussion yesterday during that same session. So in general, ISPs who are advertising sub-prefixes, and some do, and they have some legitimate reasons. And one of the other reasons that they do that is for security reasons. And when we discuss later on AS origin validation, you will find out why that's the reason. Even though it's not really a good solution, but it's a kind of a way of dealing with security. But there are other solutions now, so you don't need to do that. Some registries, particularly EPNIC, is assigning /24s because of exhaustion, obviously. But in most cases, it is smaller, bigger chunks than /24s. But right now, there are about 250,000 /24 prefixes in BGP. And we will see some of those data later on. So here is a bad example. In this particular case, the AS100 is assigned a /19 address, 100.10/19 address from RIR. Then it gives /23 address to the customer. Now, when AS100 advertises this prefix to other peers or other transit providers, it doesn't need to advertise the specific address that it assigned, sub-prefix that's assigned to its customers. Like, for example, it shouldn't advertise 10.10.0/23, but that's what it's doing right here. And what's the problem with this? Now the problem, keep this in mind. Now we have /23, 110.10.0/23 assigned to that specific customer. Now let's see what happens when the interface between the customer and AS100 goes down and come up again. So when the customer link goes down, the service provider has to withdraw that route from the rest of the internet. So even though it is in its own address block, it's withdrawing it because it has already advertised it, so it's withdrawing that specific route from the rest of the internet. So causing ripple effects throughout the internet, and everybody else also withdrawing that route, and some of them also applying route dampening to it. So later on the link comes back. When the link comes back now, it has to advertise it. So when during withdrawal, it takes a while for the route to be propagated throughout the internet. And also when, when it's advertised, it also takes same amount of time, in some cases longer, because of route dampening in some cases, even though that's becoming rare. Now, when the interface comes back, the service provider re-advertises the link, that specific network again. It propagates and then eventually reaches the rest of the internet, but it takes time. So the problem with here is two main problems. One, it caused instability on the internet, even though withdrawal of one network is not really huge, but when that adds up from multiple service providers, it's a huge problem. So it creates instability to the internet, the rest of the internet. Second, it also delays the convergence time for the customer, because for the customer, when the link comes up, the customer doesn't get the traffic immediately because the route has to again be re-advertised and propagated, and it will take time for the customer to receive the traffic. So it's bad for the customer, it's bad for the internet community, so it doesn't have any advantage. So again, the aggregation, sending sub-prefixes has some advantage for traffic engineering, but it's not this way that you do it. So we'll discuss that later on. So now instead of that, if AS100 advertised that whole block, the /19, and let's see what happens when the event happens again, when the link goes down and comes up. Now, when the link goes down, the /23 becomes unreachable within AS100, but it's not propagated to the rest of the internet. The rest of the internet only sees the /19. So traffic will come, get to AS100, and if it is for that specific prefix, it will be dropped within AS100, but there is no any route propagation outside that ASN. Now let's say the link comes back. When the link comes back, now within that S, it becomes immediately reachable because it's directly connected, it becomes immediately reachable. The rest of the internet already has a route to that prefix because it has the /19 route. So the customer gets the traffic immediately. So by doing this, you reduce the churn on the rest of the internet, you increase the quality for the customer, which is getting faster convergence. So in summary, a good example is aggregate, because it adds stability to the internet. Reduces the size of the routing table, because when you advertise multiple sub-prefixes of that /19, you are increasing the size of the internet table. It also reduces routing churn. It improves the quality for the customer because it gets faster convergence when the links comes up. So the bad example has the opposite effect, obviously. And why do people do that, even though it's really bad to do that? In some cases, it's lack of knowledge. In some cases, just you have gone that path and rolling back becomes tough, operationally challenging, and not taking the right set of steps to deal with that. But the right way is do not advertise the customer prefix routes that's assigned from your own block to the rest of the internet. If you have any questions, please feel free to ask at any point. So one key thing is some operators do not understand, most do, but some people do not understand the difference between IBGP and eBGP. IBGP is where you carry all the internet as well as the internal network. eBGP is where you apply policies and limit the amount of routes you exchange, only to those necessary, receiving only the internet table and sending only your own table, or the RIR blocks, or in the case of traffic engineering, sub-blocks that are set, that are defined for traffic engineering purpose. But the key is do not do traffic engineering on the customer sub-prefixes. Do traffic engineering on sub-prefixes that are specifically created for traffic engineering purpose. So this is today's internet table. It has reached 500,000, close to 500,000 for under 90. And if you look at that, you will see that if we aggregate it based on the CIDR block, based on the RIR assignments, you will get almost half, you will reduce it by almost half. If you do actually maximal aggregation based on the origin S, you can actually reduce it even further, down to 200,000. So even by close to 60% reduction. And you can see that more than half of the routes on the internet are /24. Even though /24 assignment is very rare. Most of the assignments are /22 and smaller, but you will see /24s a lot because of deaggregation, because in some cases for legitimate reasons to do traffic engineering, but in other cases just without doing due diligence, essentially. So when the CIDR block started, the swamp where you see a lot of routes assigned was from the 192/8, but and you can see that here, so the 192/8 in 1999 was about 6,000, and most of the other blocks were empty or very few. But that has changed a lot, and you can see now there are several swamps where a lot of routes originated. Okay. So you can see the RIR space shows creeping the aggregation, but on the other hand, you can see that people are paying more attention, and the growth, as was demonstrated yesterday, in the BGP in 2013, the growth has become linear instead of exponential. So we are actually making significant progress in terms of reducing the size of the internet routing table. So we are seeing a lot of new swamp space that we saw in the previous slide. So efforts to improve aggregation. There was an effort that was started by Tony Bates and later on revised by Philip Smith. And Philip Smith used to deliver actually this tutorial. So I took most of the material from him. And now that's being combined by Geoff Houston, who did the BGP in 2003 yesterday. And you can look at the ciderreport.org websites, most of that effort. So the results of that data is sent on a regular basis to a mailing list. It lists the top 30 service providers who could do better in terms of aggregating, and we'll see some of that data. And there is also a routing working group focusing on that, and you can look at that particular website. So, so it computes the size of the routing table, assuming, so it has the size of the routing table, and then based on the BGP attributes, it computes what would be the routing table size if we do optimal aggregation. So it gives that data, and we'll see some of that data. You can do a search, you can do computation and aggregation on the website. So it's good to go through that and see some of the data points. So here is some of the data points. So here you can see that the BGP table at different dates. This is for the week, essentially, last week, essentially. So you can see the total prefixes on the internet. And on the right, if we do proper aggregation, it will reduce the size to that value. So this is on, so you can, this data is generated on a daily basis. So if you go to the website, you'll find for this week. Also, on the summary, you see total number of ASs, the AS summary. It shows you the ASs that are advertising only a single prefix, which is a good practice essentially if they have just one prefix block assigned. The largest number of prefixes announced was by Windstream, and that's 4,500 essentially. And largest address span means the longest prefix assigned, and that the prefix advertised is that much. Okay. And here is from the same website. Here is another view. This shows you the aggregation summary, and it lists. This basically lists those who can do better aggregation. So they are ranked on the what it would be, from a better aggregation perspective. So in this particular case, net services, if they do the aggregation based on the blocks, the assigned blocks, the size of their prefixes announced could reduce by 97%. So it could go from 3,400 to 84. So significant reduction. So these are the top 30 listed. This is total count. So it doesn't mean that, it means that they are advertising the largest number of prefixes. So as you can see, Windstream is advertising the largest number of prefixes, which is 4,500, followed by net services, which is 3,400, and so on. So this data is sent regularly to the mailing list. Okay. So this is, again, Top is advertising more specific prefixes. Again, more specific than the assigned block. It pretty much aligns with the previous one, but it's slightly different, because if you are assigned /24, you may have large number of blocks, /24 blocks, but that's what you are assigned. But in this particular case, this is more specific than the blocks assigned, and that's, again, Windstream tops that as well. This shows you, again, from Windstream, what could be in terms of aggregation, how it could improve in terms of aggregation. So you can announce those withdrawals and so on. By doing that, you can decrease the number of prefixes advertised. So it's just kind of a recommendation. So importance of aggregation, size of routing table. Router memory is not a big problem nowadays because memory is not expensive. So you can have a router with very large memory. But if you have a router a legacy router that has been running on your network for quite some time, it may not have enough memory to carry the full internet routing table. So you can have a router that can carry more than multiple millions, and that's basically what most of the routers today can do. But the key is convergency. So your convergency is proportional to the size of your routing table. When you have large number of routing tables, you will have large events, the convergency will take longer. So even that, since CPU speed is also increasing from time to time, the routers can still converge in a shorter time than they could in the past because newer routers have faster CPU, they can converge faster. But the requirement also on the internet is becoming more stringent. People expect faster convergence when things happen. So because of that, it's important to keep the routing table as small as we can, while at the same time achieving the traffic engineering capabilities and other aspects to reduce the CPU load and improve the convergency time. This is the convergency reports. This is Potaro.net's website. So this tells you, it ranks the ASNs with the most instability, essentially. So that's basically how many prefixes out of their prefixes have been withdrawn and re-advertised. So that's the measure of instability or routes changed. So if your network, if there's a churn in your network that are changing several things, then obviously there's expectation that there will be some changes, but it's important to make sure that the change in your network doesn't impact the rest of the internet. In some cases, it's unavoidable, but whenever it's avoidable, there are techniques to avoid it, try to minimize the impact on the rest of the internet. So again, this is the 50 most active AS for the last 7 days. Ranked. So this is for the last 7 days, and it's the same table essentially. So in summary, aggregation on the internet could be much better. It can be reduced as much as by half, essentially, close to half, but quite easily to 35%. And there are tools to do it, and web pages to help with that. Any questions? So in this section, what we'll discuss is what kind of due diligence we need to do while receiving prefixes from peers or customers. So there are 3 scenarios for receiving prefixes from other ASNs. Customer talking BGP, peer talking BGP, obviously peer always talks BGP, and upstream or transit talking BGP. That's also almost always the case. And each one of them has different filtering requirements. So from customers, you only accept prefixes from customers who have been assigned their own address block. So you do not receive prefixes that you have assigned to your customer. Those are your prefixes, so you advertise them to other ASs based on that. So if you assign your ISP, your customer an address block, obviously you can receive that update, but you do not advertise that specific prefix as it is. You'll advertise a bigger block to the rest of the internet. So if the ISP has not assigned the address space, if you have not assigned the address space to the customer, then, and if the customer is assigned an address from a registry, the due diligence work is to check the registry or registrar and verify whether that assigned address really belongs to that customer. And you can use whois to check that. And here is an example of a whois query. So in this particular case, it means it is assigned to the customer, so you can use it. You can re-advertise it. In this particular case, it shows that it is actually allocated to a provider. So you don't want to assign it because it doesn't belong to the customer, it belongs to a provider. So this could happen by mistake. Let's say I am a customer, I'm getting an IP address assigned to me from service provider A, and I wanted to have a multi-homing and connected to my service provider B. And if I advertise that address that was assigned from A to B, that's a violation. So it's important to check that you are not advertising somebody else's address block and receiving it from your customer. Receiving prefixes from peers. So when you receive prefixes from peers, typically you exchange your own routing tables, so your own address space, and your own customer address space. So if I'm exchanging routes with ASN2 as a peer, I'll advertise the address block that's assigned to me as well as the address block that's assigned to my customers. And same thing from the other service provider. They will do the same thing. So also there, it's important to verify that the address space that is assigned to the service provider is coming from that service provider. So it's important to check the registry in that case. And in this particular case, the list may change over time. So it may become complex to manage it. So there are other tools to deal with that, and we'll discuss that. So one way is this is very static. One way is you'll have a mutual agreement with your peer. You'll have even records of that mutual agreement in the form of email or some other mechanism, and then you'll decide you will exchange this set of routes, and then you will only allow those set of routes from one another. There is another way to check the internet routing registry, and there's a link there. And the third way is, and becoming now the main mechanism, is to use origin AS validation. But this is a new mechanism. It's not yet supported by all vendors. The last time I have checked, some vendors haven't yet supported it, but they will eventually support it, and probably by now most of them may have supported it. But the route origin validation that we'll discuss, the origin AS validation that we'll discuss later on, will verify that that specific address is really assigned to that particular AS, origin AS. Not necessarily the advertising AS, but the origin AS. So the origin AS is a critical part. Okay. From upstream providers, that's your transit provider. If you are multi-homing to multiple transit providers, obviously you have to receive the full internet table from each transit provider. If you are if you are receiving transit service from one service provider, then you can just receive default from that service provider. You don't need to receive the entire internet routing table from that service provider. If you are multi-homing, having the full table allows you to do traffic engineering and also more reliability in terms of getting the shorter paths, better quality, and so on. However, if you are just peering with one customer, even if you are peering at multiple locations with one transit provider, it may be better to use default routes or just few prefixes instead of the full internet table. Okay. So when you receive, if you are receiving full table, you have to take care of some specific things. Don't take everything for granted, right? Transit providers typically are tier 1 or tier 2 depending on where you are in the hierarchy, but it's important that you have to assume that they may make mistake. So it's important to do additional filtering. So make sure when you receive updates, you don't receive default routes. So filter out any default routes. Make sure they don't send you your own prefixes. So if they are sending you the internet table, they will be most likely be sending you your prefixes as well. So your filter should make sure that you are blocking your prefixes, because you don't want to send traffic to your transit provider for your own prefixes. Doesn't make sense. Don't accept private IP addresses. So by mistake, it's possible that the service provider may inject their own private IP address that they are using internally for their own purpose. So normally they don't, but in case if they make mistake, it's important to filter those. So there is a the next one explains. So there is so bogons, so including private IP addresses, certain prefixes that are not supposed to be advertised between different ASs, and you can get that list from the that website, Team Simro. I know it's pronounced differently. I forgot how it's pronounced, but you can get the list from that website, from the Team Simro website. The same set is available for IPv6. Also, that same website provides a route server that advertises bogons. So why do you use it? Instead of constantly updating it, even though it's a short list, instead of constantly updating it, you can dynamically update it by getting the lists from their route servers. So key is paying attention to prefixes that you are receiving, whether it's from a customer, peers, or transit providers, and make sure your local network integrity is preserved, that you don't receive your own prefix advertised from other networks, or you don't receive private IP addresses because you may be using those private IP addresses in your own network. So you don't want to receive private IP addresses. Make sure you filter all the bogons. So, but internet is, it's basically built based on good internet citizenship, so it's be good internet citizens essentially. Any questions? So let's move to the next section. One of questions? Okay. So let's move to the next section, which is BGP origin AS validation. This is one mechanism to verify that a prefix really belongs to that particular AS. So before we go there, let's see the reasons why this is necessary. So there were actual incidents that basically black-holed a bunch of traffic, created a black hole for a bunch of traffic because of some misconfigurations. But in some cases, some people doing it maliciously, right? So, but internet is very important, so we have to make sure that it stays healthy. So this is one mechanism, and most of this, this is done by the CIDR, the Secure Inter-Domain Routing Group, with an IETF, and an infrastructure is built to support the origin AS validation. So let's look at this particular case. So in this particular case, let's say you have a client. Client means could be a PC, essentially, which is a customer of AS10. And let's say AS20 advertises, so let's say the 192.168.10.24, even though it's not a public IP address, let's say that IP address belongs to a customer of AS40. It really belongs to a customer of AS40. But let's say AS20 advertises that same prefix and says it is my own, right? It may happen by mistake, which is common, not very common, but it's possible. But it could happen also maliciously. Now, but AS10 has no way of, at least there's no direct way of doing it, so this is one of the mechanisms to verify that. But let's discuss about the problem. So in this particular case, when AS10 receives updates from both of them, it compares the paths and then it selects the best path. So given all other things the same, one of the main decision criteria for path selection is the path length. So in this particular case, the path length to 20, AS20 is shorter than the path length to the legitimate destination, which is AS40. So AS10 picks AS20. So client that's trying to reach 192.168.10 is actually sending its traffic to somewhere else, maybe a forged service, or maybe just getting black hole somewhere there. Okay? So, but if there was a mechanism to validate for AS10 whether that AS can legitimately originate from AS20, then AS10 would block that advertisement. It will not prefer that particular path. Here is another example. In this case, it's from the same network, AS40, but AS40 has two customers, but one of them is a legitimate owner of 192.168.10. Another one is not a legitimate owner of 192.168.10, but and the legitimate owner advertised 192.168.10/24. The other customer advertised /25. Because of the longest match rule, the illegitimate /25 wins, and traffic will be black-holed to that specific destination instead of going to the legitimate traffic. So let's look at a real life example. So this was, forgot the exact time, probably 3-4 years ago. So what happened was the Pakistani government wasn't happy with the content of YouTube, so it requested its service providers, the Pakistani Telecom Network, to filter traffic going into YouTube. And to achieve that, by mistake, they ended up advertising more specific routes of YouTube's prefixes, and then advertised to the rest of the internet. And because of that, everybody else that was trying to get to YouTube was sending their traffic to Pakistan and getting blacklist. And that outage lasted probably for quite some time. Hours, if not probably a couple of days, I forgot the exact time. But it lasted for quite some time. So it was a big outage. And it's because other service providers who were receiving this prefix advertisement just trusted it and forwarded traffic to that prefix. If they had a mechanism to check that Pakistani Telecom cannot originate this prefix, then they could have blocked that prefix, right? And preferred the legitimate path from YouTube. And actually, if you Google it, you'll find the exact incident, probably how long it lasted, the outage, and so on. You'll get more specific information. So what is the origin AS validation? It's obviously being worked by IETF Secure Interdomain Routing Working Group. Some of these are actually RFCs. I haven't updated it, but some of these are already RFCs, even though they show us drafts there. But if you go to the working group, which is the ietf.org/WG CIDR, SIDR link, that link, you'll see all the RFCs that are related to, most of them are related to this particular program, which is the AS origin validation. So how does it work? There is RPKI, Resource Public Key Infrastructure. It is a globally distributed infrastructure that basically has a legitimate registry of the real owners of each prefix. So if you are the owner of a prefix, you can submit it and they will verify with the registrar, and then you will have your entry updated there. So once your entry is there, so we'll see what the entry looks like, then if somebody can communicate with the RPKI infrastructure, verify whether that is a valid entry or not, and make policy decision based on the validity of the route. So here's what the infrastructure looks like. So the middle one is a router. So the router will have two different things. So there is a BGP table and the BGP protocol itself, and there is the RPKI infrastructure which checks the validity of the specific prefix, the origin validation of the prefix. So the RPKI database has a prefix and a mask length. So and also the origin is. So it will say this prefix and this origin, this prefix can originate from this S. That's basically what the entry says. And when you receive, from a BGP perspective, when you receive updates from eBGP peer, first you check if you configure that. If you configure RPKI checking, first it will check whether there is RPKI cache that's already on the router, right? So it will check in the cache whether that ROA is valid, if it has a covering ROA. So if it has a covering ROA, then it is valid. If it has a covering ROA and the origin matches the AS number, it is valid. If it has a covering ROA and the origin doesn't match, then it is invalid. If it doesn't have a covering ROA, which means if the entry is not in the RPKI database, then the status is unknown. So it has three different states. So let's look at what happens. So on the right side, it is the RPKI database. So let's say the first example is I have a database that has 10/8/20. Even though 10 is a private IP address, this just for as an example. let's say 10/8 through 20 is AS number 100. Can originate from AS number 100. Let's say 10/0/16 up to 24 can originate from /200. And let's say 10/0/16/232 can originate from S300. Now, if I receive an update from an eBGP peer with that has the origin AS of 300 and the prefix of 10/01/24, it matches the third entry. Since it matches the third entry, it is valid. If I receive another one, AS400, it has a matching entry, but it doesn't have, it has a matching prefix, but it doesn't have a corresponding ASN number that matches that AS number 400. So in this case, it is invalid. Then, if you receive a third one which is not in the database, then it is unknown, classified as unknown. So once you have that classification, it's up to your own decision to decide what to do with it. You can decide to drop that entry. You can decide that I will not drop it, I'll accept it, but I'll have less preference over other entries. So you can say the preference will be, I'll prefer valid, then unknown, then invalid, right? So if I receive two different passes, if one of them is a valid one, another one is invalid one, even though the valid one has everything else better, the invalid one has everything else better, let's say shorter AS path and so on, you would prefer the valid one. So you'll make that type of decision. And that's a local policy that you can configure. So another important thing is the IBGP signaling of origin AS validity. So you don't want to check this on every update. So you want to check this when you receive routes from your eBGP peers. You don't want to do this when you receive routes on your IBGP peers. But how do you get the information? So the information can be signaled via the origin AS validity state. Okay? So this is a new extended community that provides this information. So the new extended community indicates whether the status of the AS origin validation, either valid, invalid, or unknown. And then based on that, you'll make a decision whether to not advertise it, not to install it, or to advertise or install it, or prefer it, less prefer it, and so on. So it will be a local policy decision. Any questions? Okay, so this is how you can. Questions?
Me? Alexander, I'm in Curator Labs. The question is, all this RPKI thing is fun and dandy, but we only have to check the origin AS. While you can insert in ASPath invalid prefixes, meaning that origin AS will be valid and fine, but the path itself will be illegitimate. Is there any movement to introduce AS path checking in the RPKI?
So that you mean the transit paths?
Yes. If you do AS path poisoning, all those things would not prevent perpetuator from executing prefix hijacking attack on you.
Okay. So, so basically, if somebody intentionally injected a route as itself in the middle, but the origin as valid origin, Yes, so that's there is no way to the current mechanism doesn't allow it. I'm not up to date on the RPKI standard, but I don't think it allows that. And I think it's a very difficult problem to solve also.
Yes, it's
because,
not...
Because it's very difficult to say this S cannot be a transit for this particular prefix.
Yes, there is no easy solution. There is no obvious solution. And on the other hand, we noticed at least a couple of times when our own prefixes were hijacked through this technique throughout this year. And I think it's going to be even worse.
Yeah, I agree. I mean, that's it's not a perfect solution. Again, it's based on, internet is based on trust. When somebody violates that trust, you can put some...
This is interesting because just a couple of weeks ago, I had an interesting conversation with someone who said that back then, when internet was created, everyone was thinking that there will be only good nodes and no evil nodes, and everyone will cooperate. But it's just not the way it is right now.
Yeah.
And we have to figure out what to do about this thing, because right now I see no easy solutions. Does someone see? Have anyone seen any papers on this subject for last year? Yes? No?
Anyone?
Nobody. That's the problem. We're on losing side. Attackers have more technological capabilities to execute this vulnerability in their favor.
Okay. I'll have a discussion later on afterwards.
Mm-hmm. Thank you.
Okay, you're welcome. Any additional questions? So the prepping the network is assuming you don't have BGP at the beginning. How do you start deploying BGP? So obviously you'll have you'll need to have ASN. You don't need a publicly assigned ASN to run BGP, but if you want to have eBGP with a service provider and originate a prefix with your own ASN, then you will need a public ASN. Okay. So there are some who use private ASN, particularly if a service provider assigns you an address from their own block. It might be better to use a private ASN number, and the service provider will strip the private ASN number when it advertises to upstream providers or peers. And obviously, it doesn't advertise that specific prefix that's assigned to you from the service provider. It will assign a bigger block. It will advertise a bigger block. So the major assumption in this case is there is no questions. So the major assumption here is the network is not running any BGP at the moment. And the network is not running any IGP, which is very unlikely. So assume that this is starting just at the beginning. No IGP, no BGP. So the first decision is whether to pick OSPF or ISIS. So I'm not bringing up RIP or HRP. These are by far the most widely used by operators, and they provide a lot more features than the other protocols. Obviously, you'll need to assign a /32. It's important for the loopback interfaces. Usually when you do your addressing, it's important to use a continuous address block for your loopback IP addresses so that you can do the specific filtering on those loopback IP addresses for a number of different purposes. So the loopback interface is used both for OSPF as a router ID, for BGP as a router ID. If you have other things like MPLS LDP, traffic engineering, and so on, they will be used as a router ID for those protocols as well. So you have to explicitly configure them to be router ID for those protocols, but it's important to use a loopback interface as the router ID. Then the next phase is you'll deploy IGP. Again, if you already have a static route, that was the assumption. If you already have a static route and you configure IGP, since in most cases static route is preferred over IGP, assuming it's the same set of prefixes, not more specific prefixes covered by the IGP, again, you will not have any impact on the current routing because your static route is still there. So it's very important to keep the link state database lean, and there are multiple techniques to do that. One way is, for example, if you have multiple links between routers, convert them into link aggregation bundles instead of having multiple layers 3 interfaces. You save IP addresses, you reduce the link states. Also, don't include your customer-facing interfaces into IGP. It's unnecessary. So you use IGP on your, mostly on your WAN links and links that are interconnecting your core routers and aggregation routers. Unless you have a very big network, it's usually better to use a single area, both in the case of ISIS as well as OSPF, than using multiple areas. Multiple area means suboptimal routing. It helps you scale up, but you'll have suboptimal routing. So if you want to have an optimal routing in your IGP domain, keep it one area. Obviously, if you have a very big network, you cannot have one area, you have to split into multiple areas. So prefixes such as DHCP assigned IP addresses like DSL, cable, DL, and so on, or BIRAS, those IP addresses should not be injected into IGP. They should be carried in IBGP, not in IGP. Hosting LANs, the static and hosting LANs, again, those should not be in IGP. Customer assigned IP addresses, also they should not be in IGP. They should be in IBGP. So the second step after you configure your IGP is your IBGP. So you will create a full mesh IBGP. Obviously, you don't want to have, you don't want to start with full mesh. It's better to use route reflectors, but it's important that every router in your core, not every router in your network, but every router in your core should, at least routers that are used for transits between different service providers, should be in IBGP. So here are some examples. In this case, for example, A and B, if you are a transit path, if AS200 is a transit path, A and B need to have the full internet table. So they have to be running IBGP, as well as they have to receive the full tables. Routers C, D, and E, they may need to be in IBGP. If you are carrying other prefixes in IBGP, like DSLAM and so on prefixes in IBGP, then those routers also need to be in IBGP. Others, if that's not the case, then they don't need to be in IBGP. They can just stay in IGP. So typically, depending on your network, you will have different layers. Core, distribution, aggregation. You may have a collapsed two-layer network. You may have even additional layers, super core, core, distribution, and aggregation, depending on your network and how to evolve it. The backbone is usually, or the core, which is a backbone, is usually a transit. So if you are a transit provider, traffic coming from one S and transiting through your network to another S only goes through the core. It doesn't go through the distribution or aggregation. So the distribution is the middle, and or the pop aggregation, and then the aggregation is the edge where you have the DSLAMs and everything else. IBGP is optional in that if you only have one router doing, or one or two routers doing full internet routing table, those two routers can just run BGP, and everybody else runs IGP and point as a default route to those two core routers. So that's possible. But if you are an ISP, if you are a transit provider, if you are providing service for other customers, then you will need IGP, obviously, IBGP, because you will need to carry those routes in IBGP. And on aggregation devices such as DSLAMs, even they may not be able to run BGP at all, in which case you don't run BGP there. You may run IGP from them to the aggregation routers or to the distribution router, and on the distribution router, you will inject it into IBGP. So the distribution router usually runs IBGP. And it's used to also inject local routes and DSLAM routes and customer routes into IBGP. The core usually is a transit, so it has to run IBGP. So you have to decide on IBGP policy, whether to use IBGP everywhere or partial or mix. Also in terms of whether your IBGP routers will carry the full internet table or partial table or a mix. In some cases, you will have to decide what type of communities you want to use, whether to use route reflectors. You have to come up with your own community policy. Route reflectors, you have to generate configuration templates, and we'll discuss some of those. Then you deploy IBGP. So the first step is whether to decide a full mesh or use a route reflector. This particular example assumes a full mesh. And you have to make sure that IBGP distance is greater than IGP, and usually that's the default. Since you are injecting IGP routes into IBGP, you don't want to prefer the IBGP route over the IGP route, so the distance for IBGP should be higher than the distance for IGP. By default, that's typically the case. So inject customer prefixes using using different techniques. One of them is using a network statement. You'll need to have a corresponding prefix in IGP, either using a static route or in your IGP, but to inject it into IBGP, you will use a network statement. And when you use a network statement, its origin will be set as IGP, which is preferred. So once you implement IBGP, once you implement IGP, you can now remove static routes one by one from your network and fully go to both IBGP and IGP routing. The next one is to implement eBGP. So for customer prefixes, if customers are assigned IP addresses from a registry, you will obviously be running eBGP with them. If they are multi-homed, if they are not multi-homed, you don't need to do eBGP. But if they are multi-homed, or if they have a corresponding ASN number, then it's important to run eBGP and inject using eBGP. For customer-facing point-to-point links, the links that are shared between you and your customer, you don't need to inject them into IGP. You can inject them into IBGP, and you can use a network statement or a distribute command to inject them. The same thing with DHCP assigned IP addresses, BRAS IP addresses, and local LANs. You can inject them either using redistribute commands or using network statements. Usually prefer using the network statements. So this is just removing the static routes. And when you remove the static routes, you don't need to remove all of them at the same time. You can remove some and then check, and then remove some and check, verify everything is working. Check the RIB and make sure that now IGP is preferred over IBGP, and so on. So the key is all the steps specified previously, they are not flagged, so you don't have to do them at once. You can implement each one of them gradually over time, verify that everything is working, and including removing the static routes, you can do them over a longer period of time. And that's a good practice instead of doing it just everything at once. Okay. Any questions? Okay, so configuration tips. So some reviews. Make sure that you have a loopback interface, and make sure that your IBGP sessions are between loopback interfaces. If you don't explicitly specify them, the default may be some outgoing interface IP address. So make sure that you explicitly specify that you are going to use the loopback IP address for peering. And make sure that those loopback IP addresses are injected into IGP. For the DMZ nets, the nets that are connecting your network to another ASN, you can use unnumbered interfaces, or you can use a private IP address for them. As long as you override the next hop to be the loopback IP address. So for routes that you advertise to your IBGP peer, so if you receive a route from eBGP and advertise to IBGP, the default is you will preserve the next hop, which is the interface IP address of the DMZ. But the recommended way is to override that with the loopback IP address of the router. So when you do that, you can use private IP address for that particular interface, or you can use public IP address. In most cases, that's the case, but you don't need to inject it into IGP. You can inject it into IBGP for troubleshooting purpose, but you don't need to inject it into IBGP. Sorry, into IGP. So the BGP, the next hop self means when you are sending updates to your IBGP peer, instead of preserving the next hop, which is the IP address of the peer router, you can override it with next hop self, which means the next hop becomes a loopback IP address of the router. And that is the recommended behavior to avoid injecting the DMZ nets into IGP. Also, it increases stability. So limiting AS path lengths. So the reason that you want to be careful when you are prepending or adding AS-PAS lengths is some implementations have limitations in terms of how many AS-PAS you can accommodate in the update. The standard doesn't say what should be the maximum supported, but implementations have their own maximum, and you may hit that maximum, and it's important to understand what the implementation maximums are. But in general, it's not a good practice to reach that maximum anyways. So when you do prepending to increase the lengths and do traffic engineering, do not prepend a huge number of AS prepends. Do a manageable number while achieving your traffic engineering. So the average AS-PAS length on the internet is 3.8. That's amazing. It means everybody is very close to one another. So you are, on average, 4 AS hops away, right? So that tells you there's a lot of interconnection between ASs. The maximum AS-PAS, unique AS-PAS is 13. But the maximum prepend observed was 34. That's huge. I mean, the maximum unique is 13, but somebody, even if the maximum unique was still there in that particular case, you still have more than 20 prepended in the AS-PAS prepend, which is not really necessary to achieve the traffic engineering, but it could hit some of the limits on some of the routers on the internet. So here are some examples that shows huge, ridiculously long AS numbers, and in this case, all prepends. Another general practice is when you have eBGP peering, use GTSM or generalized TTL security mechanism. So if the two peer routers can support GTSM, the advantage of GTSM is that somebody cannot establish eBGP peering with you or send you an eBGP update using an existing TCP session because the TTL is set to be 255, and if you receive an eBGP update with a TTL number greater than 255, it will be dropped. This is what the GTSM does. And some platforms implement that in hardware. So the packets dropped in hardware, no CPU impact, no flapping of BGP sessions. If somebody tries to attack your BGP sessions, one way is to send you a BGP update that masquerades to be from the IP address of, it uses a forged IP address, which is your directly connected peer, but it's actually coming from far away. So when that happens, the TTL by then has reduced to less than 255, so it will be dropped. So it's important to implement, if it is supported, implement GTSM. So in some cases, it's just called TTL security or BGP TTL hack. So the generalized mechanism is not just only for BGP. It can also be applied to other protocols, including OSPF. That's why it's called generalized. And it is also applied to BFD and other protocols as well. Also, in addition to GTSM, it's important to use, to have additional, it's good to have multiple layers of security, so use password protection for your BGP sessions. Templates are important. So with templates, you create a template for all your IBGP sessions and use that template instead of writing a specific session for each eBGP peer or for each IBGP peer. By doing that, you make the configuration manageable, reduces the potential for mistakes, and increase stability and scalability. So some recommended templates are available on the Team Simru site. Again, I forgot how to pronounce it, but it's not pronounced that way. So same thing for a typical IBGP template will have next hub self, and also enable sending communities. Okay? If depending on the platform, some platforms or some implementations may not support sending community by default. So you have to make sure that either the default behavior is supported or explicitly specify that you are sending community. And communities are important for policy, so it's important to send communities. In some cases, you can specify the BGP version. If that's the case, make sure you explicitly mention that it's BGP version 4, even though there are very few implementations that are supporting other than BGP version 4. So if the implementation supports other versions, explicitly specify version 4. But that's very rare nowadays. Again, for IBGP, even though it's your internal network, still it doesn't hurt to use additional security, which is password protection for your IBGP session. Remember that you cannot use the TTL security mechanism for IBGP because IBGP spans multiple hubs. So you cannot use TTL mechanism to protect IBGP sessions. For eBGP templates, make sure you remove private ASN numbers if it's not the default behavior. Remove bogons. Use extensive backup filters. If you use communities to filter, also use prefix list to filter. Also use ASPAS filtering to filter. It doesn't hurt if you are filtering the same thing with multiple filters. It's good to have backups. Again, use GTSM if it is supported. If the peer supports it, use GTSM. We're almost there. Use the maximum prefix tracking, because in some cases, somebody may inadvertently send you huge amount of prefixes, including their own prefixes, and it may overwhelm your routers. So in that case, it's good to use a maximum prefixes, which means if somebody sends you more than what you configured as maximum, the session will be reset automatically. You can also limit the maximum ASPAS lengths, log changes to neighbor. So that is just to see when neighbor goes up and down, you generate a log message and the log will be logged so that you can eventually troubleshoot if there was any flapping. So in summary, it's important to use BGP configuration templates, standardize on templates for IBGP, for eBGP. There may be some variations for different types of IBGPs, for different types of eBGPs, but the key is it's important to use templates and use standard tricks, including TTL security and other mechanisms to make sure that your eBGP peering as well as IBGP peering is secured, and use anything that makes your life easier, which is basically the configuration templates and using communities. Those are very important to scale from a configuration perspective and from a troubleshooting perspective. So it's all about, BGP is all about scaling, particularly when you have a large number of routers. We are done with the presentation. Questions? Any questions? All right, thanks.